Good evening. Get comfortable, close your eyes, and prepare for a journey into the darkest corners of our universe. Take a moment to imagine everything you can see. Stars, planets, galaxies, nebulae. All this splendor, all the matter we know and from which we are made, accounts for only about 5% of the entire universe. 5%. So, where is the remaining 95%? A significant portion of that, about 27%, is something scientists call dark matter, a substance that no one has ever seen, touched, or measured directly. Yet its gravitational influence is so enormous that this invisible entity acts as the true conductor of the cosmic orchestra. It dictates how galaxies rotate, how they cluster together, and how the universe is structured on the largest scales. Today, we will dive into this great mystery. We will try to understand how we can detect the presence of something completely invisible and why this enigma remains one of the most vital and exciting puzzles in modern science. Prepare yourselves. Our journey into the realm of darkness begins. The story of dark matter's discovery is a classic scientific detective story, one that began almost a century ago. In the 1930s, Swiss astronomer Fritz Zwicky, a man known for his rather eccentric personality, was studying a massive collection of galaxies in the Coma cluster. He was measuring the speeds at which individual galaxies were moving within this cluster, and that's when he encountered a paradox. The galaxies were moving so fast that the gravitational pull from all the visible matter, all the stars, gas, and dust within them, was nowhere near enough to hold them together. According to his calculations, the Coma cluster should have long ago spun itself apart, scattering into space like a poorly constructed carousel, turning at maximum speed. To explain why the cluster still existed, Zwicky hypothesized that there must be some hidden, invisible mass present which he called dunkle Materie, German for dark matter. He believed its gravity acted as the glue holding the entire cluster together. However, at the time, the scientific community treated Zwicky's radical ideas with considerable skepticism, to say the least. He was widely regarded as an eccentric, and his findings were dismissed as calculation errors. It took nearly 40 years before the idea was taken seriously again, thanks to the work of another pioneering astronomer. So, let's dive into Chapter 1 of our investigation, titled The Ghost in the Galactic Carousel. Back in the 1970s, American astronomer Vera Rubin, working alongside her colleague Kent Ford, was meticulously observing spiral galaxies, much like our own Milky Way. They wanted to understand how fast stars were rotating based on their distance from the galactic core. According to the established laws of physics, the ones we've known since Newton, stars on the outskirts of a galaxy should be moving much slower than those closer to the center, where the bulk of the visible mass is concentrated. Think of our own solar system. The farther a planet is from the Sun, the slower it orbits. Mercury zips around incredibly fast, while distant Neptune moves at a much more leisurely pace. Everyone expected to see a similar pattern play out in the galaxies. What Vera Rubin discovered, however, completely defied all expectations. Stars on the furthest edges of these galaxies were rotating at the same speed, and occasionally even faster, than the stars right near the core. This was utterly inexplicable. It was like spinning a carousel and finding that the horses on the outer rim were moving just as fast as those near the central pole. The only way to keep them from being flung into space would be to add a tremendous amount of invisible mass whose gravity would hold everything together. Vera Rubin's work became the first, undeniable, widely accepted proof that the astronomer Fritz Zwicky had been right all along. Galaxies are filled with an invisible substance whose mass is several times greater than the mass of all the visible stars combined. An illustration for this block would show the expected galaxy rotation curve, which drops off with distance next to the actual flat curve that Rubin observed. This flat curve is the definitive smoke pointing to the fire of invisible matter. This discovery became a crucial turning point in cosmology. Scientists were forced to realize that the universe was far more intricate than anyone had ever imagined. After Vera Rubin's pioneering work confirmed the existence of this anomaly, scientists were confronted with the obvious question: what if we're simply missing something? What if this dark matter wasn't some exotic, mysterious substance, but just a huge collection of ordinary, but extremely faint or invisible, objects? This idea became the foundation of the MACHO hypothesis: massive, astrophysical compact halo objects. Despite the complex name, the objects themselves were straightforward. Things like cooled white dwarfs, neutron stars, stellar mass black holes, or the so-called brown dwarfs, failed stars, that are simply too small to ignite thermonuclear fusion in their cores. Theoretically, if the halos of our galaxy and others were absolutely packed with these kinds of objects, their combined mass could account for the observed stellar rotation speeds. Crucially, this was a hypothesis that could be tested, and the verification method was incredibly elegant. The mechanism was this: if one of these massive compact objects passed directly between us and a distant star, its gravitational field, as predicted by Einstein's theory of relativity, would act like a lens, briefly magnifying and brightening the background star. This phenomenon is known as gravitational microlensing. Throughout the 1990s, several large-scale projects were launched, monitoring millions of stars in neighboring galaxies for years, hoping to capture these events, and they did find them. But there were tragically few. Observations conclusively demonstrated that MACHO-type objects could only account for a tiny fraction of the necessary hidden mass. There simply aren't enough of them to explain the dark matter effect. Thus, the MACHO hypothesis was largely debunked. It became clear that the answer would not be found among ordinary astronomical objects. The solution must lie in something entirely different, something that is not composed of the familiar protons, neutrons, and electrons. Dark matter is not just dim, it is fundamentally new physics. When it became clear that dark matter wasn't composed of conventional matter, scientists began sketching out its profile, what we know about this elusive substance. So, what can we deduce about it without ever seeing it? Firstly, it is, quite literally, dark. This means it doesn't emit, absorb, or reflect light, or any other electromagnetic radiation for that matter. It's completely transparent to photons. If you could actually hold a chunk of dark matter, it would be utterly invisible, with light passing straight through it without impedance. Secondly, it interacts with normal matter exclusively through gravity. In fact, it's these gravitational effects that were our only clue for detecting it in the first place. This is its single known manifestation. It pulls on stars, galaxies, and even light itself, but it doesn't engage in any other fundamental interactions. Thirdly, it has to be cold. Now, in cosmology, cold doesn't mean low temperature in the everyday sense. It means that the dark matter particles are slow-moving, way below the speed of light. Why is this distinction crucial? Because only slow-moving matter can efficiently clump together under gravity, forming the massive halos in which galaxies eventually emerge. If dark matter were hot, meaning its particles were zipping around at near-light speeds, they would simply disperse, unable to form sufficiently dense structures. Simulations of the large-scale structure of the cosmos show us clearly. Without cold, dark matter, we would not see the intricate cosmic web of filaments, galaxies, and clusters that we observe today. The universe would be far more uniform. Finally, dark matter must be stable. It has survived since the earliest moments of the universe and hasn't decayed over the nearly 14 billion years that have passed. So here is the profile of our suspect. An invisible, gravitating, cold, stable substance composed of particles that fall outside the parameters of the standard model of particle physics. This is no longer just a fuzzy hypothesis, it's a rigorous set of demands that any true dark matter candidate must satisfy. Shifting gears to a much grander scale, another incredibly powerful tool for studying dark matter is gravitational lensing. But this is far bigger than the microlensing we just discussed. Imagine looking at a distant galaxy. If a massive concentration of matter, say an entire galaxy cluster, sits directly between you and that distant object, its gravitational field acts like a gigantic cosmic lens. According to Einstein's general theory of relativity, Massive objects warp the fabric of space-time around them, forcing light passing nearby to travel along these curved paths. As a result, the image of that distant galaxy gets distorted. It might stretch into a long arc, appear doubled, or even be pulled into a perfect circle known as an Einstein ring. The strength of this distortion is directly dependent on the total mass of the lensing object, and this is where the real fun begins. Astronomers can observe a galaxy cluster, estimate its visible mass by counting all the stars and gas, and then see how strongly that cluster is bending the light from objects even further away. Time and time again, the observed distortion proves to be far stronger than what the visible matter alone could produce. This means the cluster contains a massive amount of additional, invisible mass that is creating this powerful lensing effect. Furthermore, by analyzing these distortions, scientists can map the distribution of all the mass in the cluster, both visible and dark. These maps clearly show that the majority of the mass isn't concentrated where the stars are. Instead, it resides in an enormous diffuse halo of dark matter surrounding the visible galaxies. One of the most compelling examples of this technique is the bullet cluster, which is the result of two galaxy clusters colliding. Images show that the hot gas, the visible matter, slowed down and accumulated in the center during the crash. However, gravitational lensing maps reveal that the bulk of the mass, the dark matter, passed straight through one another without slowing down, ending up on the outer edges. This provides direct, stunning evidence that dark matter interacts with almost nothing except gravity itself. Beyond galaxy observations, there is an entirely separate and independent source of data pointing to the existence of dark matter. This is the cosmic microwave background, or CMB. It is essentially the echo of the Big Bang, the light from the very early universe captured when it was only about 380,000 years old. Before that point, the universe was so hot and dense that it was an opaque plasma of protons, electrons, and photons. Once it had cooled sufficiently, protons and electrons were able to combine into hydrogen atoms, and the universe suddenly became transparent. The light that had been trapped within the plasma could finally travel freely, and today we observe it as microwave radiation coming from every direction in the sky. This radiation isn't perfectly uniform. Its map reveals tiny temperature fluctuations, speckles that are just 1/100,000th of a degree hotter or colder than the average. These fluctuations are the direct imprints of the very first density variations, the seeds from which today's galaxies and clusters ultimately grew. By analyzing the size and distribution of these speckles, scientists can determine the precise composition of the early universe with incredible accuracy. It's like being able to deduce the nature of stones thrown into a pond just by observing the pattern of the ripples they create. So what do these data tell us? They reveal that for the observed pattern of fluctuations to have formed, the ordinary baryonic matter, the stuff we are made of, could only account for about 5% of the total energy density of the universe. Another 27% had to be cold, dark matter. The remainder is dark energy. These figures, derived from observing the earliest universe, strikingly match the figures we get from observing modern galaxies. These are two completely independent methods pointing to the exact same conclusion. A consistency like this provides extremely strong evidence that the cold, dark matter model is correct. Without it, we simply cannot explain either the rotation of galaxies or the observed structure of the cosmic microwave background. So we have established two things. Dark matter exists and it is not made of conventional particles. This realization opens the door to an entirely new, unexplored realm of physics, the physics beyond the so-called Standard Model. The Standard Model is the theory that brilliantly describes all known elementary particles, quarks, leptons, and bosons, and three of the four fundamental forces, the strong, weak, and electromagnetic interactions. However, it contains no particles suitable to be the cold, dark matter we observe. Essentially, dark matter is our clearest window into new physics. And theoretical physicists have proposed countless hypotheses about what this new particle might actually be. For many years, the most popular and most extensively studied candidate has been the WIMP, or weakly interacting massive particle. According to this theory, WIMPs are heavy, perhaps 100 times more massive than a proton. They do not participate in the strong or electromagnetic interactions, hence why they are dark, but they do participate in the weak nuclear interaction, the same force responsible for certain types of radioactive decay. Why is this hypothesis so appealing? Because of the so-called WIMP miracle. Calculations show that if these particles existed in the early universe in thermal equilibrium with everything else, their quantity would have naturally decreased as the universe expanded and cooled. This decrease was due to annihilation, where two particles collide and transform into others. Critically, the calculations predict that exactly the right number of WIMPs would have survived this annihilation process to explain the observed density of dark matter today. This numerical coincidence seems far too elegant to be pure chance. Furthermore, many theories that extend the standard model, such as supersymmetry, naturally predict the existence of such particles. Supersymmetry proposes that every known particle has a heavier superpartner. The lightest of these superpartners is usually stable and possesses all the necessary characteristics of a WIMP. Thus, the WIMP hypothesis doesn't just explain dark matter, it simultaneously solves several other outstanding issues in particle physics. If WIMPs actually exist, then even with their incredibly weak interaction, there has to be a way to find them. As we speak right now, the Earth is hurtling through the vast halo of dark matter that envelops our Milky Way galaxy. This means billions of these hypothetical particles are streaming through our bodies and the entire planet every single second. The core problem is that they interact with almost nothing at all. The chance of a WIMP hitting an atomic nucleus in your body is vanishingly small, but if you use a very large detector, one containing a massive number of atoms, and wait for a very long time, you might just register one of those collisions. This is precisely the principle behind direct dark matter detection experiments. To eliminate the background noise from cosmic rays and natural radioactivity, which could mimic a WIMP signal, these detectors are built deep underground, in former mines or beneath mountains. The rock itself acts as a natural shield. The detector itself is usually a massive tank filled with ultra-pure, liquefied noble gas, such as xenon or argon. When a WIMP, having traveled from deep space, finally manages to strike a xenon nucleus, it transfers a fraction of its energy. The recoiling nucleus produces a tiny flash of light, a scintillation, and frees up a few electrons. Sensitive photodetectors placed above and below the tank register both the light and the electrons, allowing scientists to precisely pinpoint the location and energy of the interaction. The most famous experiments of this type include Xenon T in Italy, Lux Zeppelin, LZ, in the United States, and Pandax in China. They have already achieved incredible sensitivity, but so far they haven't detected any conclusive WIMP signals. This silence is forcing scientists to either revise the properties of WIMPs or more actively explore alternative hypotheses. Perhaps WIMPs interact even more weakly than we assumed, or maybe their mass lies in a completely different range. Or perhaps dark matter isn't WIMPs at all. Beyond direct searches, scientists employ an indirect method to hunt for WIMPs. The basic concept is this: while WIMPs rarely interact with ordinary matter, they should, from time to time, collide with one another. This is expected to occur more frequently in areas with high concentrations of dark matter, such as the center of our own galaxy or the cores of dwarf satellite galaxies. When two WIMPs collide, they can annihilate, that is, disappear, converting their mass into a burst of standard model particles, photons, specifically gamma rays, as well as neutrinos, electrons, and positrons. It is these annihilation products that we attempt to detect using our sophisticated telescopes. For instance, space-based gamma-ray telescopes, such as the Fermi-LAT, continuously scan the sky, searching for any excess of gamma rays originating from the galactic center. If we detected a signal there that couldn't be accounted for by known astrophysical sources like pulsars, black holes, and so on, it would be a potential signature of dark matter annihilation. Neutrino telescopes, such as the Ice Cube Observatory in Antarctica, employ a different strategy. They search for neutrinos that would be produced by WIMPs annihilating after being gravitationally captured by the Sun and accumulating within its core. Over the past few years, we have seen several intriguing hints and anomalies in the data, most notably a gamma-ray excess emanating from the galactic center, whose characteristics closely matched what we might expect from WIMP annihilation. However, subsequent analysis showed that these signals could likely be explained by more mundane astrophysical sources, for instance, a large population of previously undiscovered millisecond pulsars. To date, however, conclusive proof of dark matter annihilation remains elusive. Just as with direct detection efforts, this great silence challenges the simplest WIMP models and compels physicists to broaden the scope of their search. The third front in the hunt for dark matter is happening right here, at the most powerful particle accelerators, such as the Large Hadron Collider at CERN. The fundamental concept is the exact opposite of looking out into space. If WIMPs naturally annihilate and transform into standard matter, maybe we can smash ordinary particles together at tremendous energy and actually create dark matter particles in the aftermath. At the LHC, protons are accelerated to nearly the speed of light before they smash into one another. This collision point releases colossal amounts of energy, which, according to Einstein's famous equation E=mc2, can be converted into the mass of new, potentially very heavy particles. The detectors surrounding these collision points register every single particle created in the process. But here's the problem. How do you spot a dark matter particle if it's invisible and doesn't interact with the detection equipment? Physicists use a clever trick. They look for events characterized by missing energy. Due to the fundamental laws of conservation of energy and momentum, the total energy and momentum of the particles after the collision must precisely match the energy and momentum before the collision. If a pair of dark matter particles are created in the smash-up, they will simply fly out without leaving any trace in the detector. Crucially, however, they still carry away a portion of the energy and momentum. The detector will record that the visible particles scattered wildly in one direction, while nothing appeared on the opposite side, as if something invisible had kicked them off kilter. This specific imbalance, known as missing transverse energy, serves as indirect evidence that invisible particles were born. These searches are actively ongoing at the LHC. Scientists hunt for events where, for instance, a powerful photon or a high-energy jet of hadrons is created, accompanied by a large amount of this missing energy. So far, however, all observed events align perfectly with the predictions of the Standard Model. No convincing signals of new physics or the creation of dark matter particles have yet been discovered at the collider. This gives us yet another piece of the puzzle, suggesting that if WIMPs do exist, their properties are probably more complex than we currently imagine, or perhaps that dark matter isn't WIMPs at all. Since the search for WIMPs hasn't yielded success so far, scientists are increasingly focusing their attention on a different class of dark matter candidates, and one of the most intriguing among them is the axion. The axion is a hypothetical, extremely light particle first proposed back in the 1970s. Crucially, it was introduced to solve a completely different puzzle in particle physics known as the strong CP problem. This problem concerns why the strong nuclear force, unlike the weak force, seems to respect a particular symmetry, CP invariance. The theoretical mechanism designed to solve this puzzle predicted the existence of a brand new particle, the axion. It turns out that this particle, conceived for entirely different reasons, possesses many of the ideal properties required for dark matter. Unlike the heavy WIMPs, axions must be ultralight, potentially billions of times lighter than an electron. Because of this minuscule mass, they behave less like individual particles and more like waves. In the early universe, they would have been produced in vast quantities. Today, they are thought to form a gigantic, coherent field that permeates the entire cosmos, a sort of invisible ocean. While individual axions barely interact with normal matter, their collective, wave-like effect might still be detectable. The key predicted property of the axion is its ability to convert into a photon and back again when exposed to a powerful magnetic field. This conversion effect is the basis for most axion search experiments. The most famous of these is the ADMX, or Axion Dark Matter experiment. This setup consists of a powerful superconducting magnet that contains a resonator, essentially a hollow copper chamber. As this detector moves through the galactic ocean of axions, Some of the particles, upon entering the strong magnetic field, should spontaneously convert into microwave photons. If we tune the resonator's frequency to match the energy or mass of the axion, a resonance will occur, allowing us to pick up a very faint microwave signal. It's analogous to tuning a radio to the right station. The major challenge is that we don't know the axion's exact mass, so researchers must slowly scan an extremely wide range of frequencies. This is painstaking and time-consuming work, but it is ongoing, and the sensitivity of these experiments is set to increase significantly in the coming years. Axions offer an elegant and beautiful alternative to WIMPs. Their discovery would truly be a double victory for physics. When considering candidates for dark matter, some ideas are far more exotic. One such candidate is the sterile neutrino. We know there are three types or flavors of standard neutrinos: the electron, muon, and tau neutrinos. These are extremely light particles that interact only via the weak and gravitational forces. For a long time, they were considered potential dark matter candidates, but it was later determined they are simply too light and too fast. They fall into the category of hot dark matter and therefore cannot account for the formation of galaxies. However, some theories predict the existence of a fourth type of neutrino, known as the sterile neutrino. It's called sterile because it participates in virtually none of the standard model interactions, aside from gravity, of course. It interacts with standard neutrinos only through a very specific mixing mechanism. If sterile neutrinos were massive enough in the kilo-electron-volt range, making them heavier than standard neutrinos but much lighter than WIMPs, they could potentially be classified as warm dark matter. They would be slow enough to form galaxies, yet they would also smooth out structure on the smallest scales. This smoothing effect could potentially resolve some outstanding issues with the standard cold dark matter model. This hypothesis comes with an interesting prediction. Although sterile neutrinos are extremely stable, they can occasionally decay, for instance, into a standard neutrino and a photon. This resulting photon would have a very specific energy, exactly half the mass of the original sterile neutrino. Astronomers are actively searching the X-ray spectra of galaxies and clusters for a faint emission line at a specific energy that would signal such a decay. In 2014, there were several reports claiming the detection of a mysterious X-ray line at around 3.5 kilo-electron-volts. This energy would be consistent with a sterile neutrino mass of 7 kilo-electron-volts. This sparked considerable excitement, but subsequent, more precise observations have failed to definitively confirm or rule out the signal. The question remains open, and the hunt for the sterile neutrino continues. Let's take a break from the world of particle physics for a moment and look at the problem from a completely different angle. What if there is no dark matter at all? What if we are wrong, not about the universe's composition, but about the very laws of gravity? All our conclusions about dark matter's existence rely on the assumption that Newton's law of universal gravitation and Einstein's general relativity hold true across all scales. However, we've only verified them with high precision within the confines of our own solar system. What if gravity behaves differently on the scales of galaxies and galaxy clusters? This idea forms the foundation of alternative theories, the most famous of which is MOND, or Modified Newtonian Dynamics. This theory was proposed by Israeli physicist Mordechai Milgram in the 1980s. Its core idea is that the law of gravity changes when accelerations become extremely small. In conditions familiar to us within the solar system, where accelerations are high, gravity behaves in the standard Newtonian way. But on the outskirts of galaxies, where stars experience extremely weak gravitational pull and thus have very low acceleration, gravity actually becomes stronger than Newton's theory predicts. This extra pull explains why stars on the periphery orbit so quickly without needing to invoke any extra mass. MOND is surprisingly successful at describing the rotation curves of a huge number of galaxies using just a single new universal parameter. It's an incredibly elegant solution. However, the theory also faces serious challenges. Firstly, it performs poorly on the scale of galaxy clusters. To explain cluster dynamics, MOND still requires some amount of missing mass, although significantly less than standard cosmology. Secondly, it cannot adequately explain gravitational lensing effects, such as those seen in the bullet cluster, where the center of mass is clearly separated from the center of the visible baryonic matter. And most critically, MOND is a non-relativistic theory, making it extremely difficult to reconcile with general relativity and cosmology, particularly the data derived from the cosmic microwave background, or CMB radiation. While relativistic extensions of MOND do exist, they are highly complex and have met with limited success. Nevertheless, the idea of modifying gravity remains on the periphery of scientific discussion, serving as a reminder that we must remain open to all possibilities. Let's return to the core hypothesis, the existence of dark matter particles, and see how this influences the evolution of the universe. Dark matter plays the role of an invisible architect, laying the foundation for all the visible structure we observe today. Immediately after the Big Bang, the universe was nearly perfectly uniform. However, it contained tiny quantum fluctuations in density. In those areas where the density was slightly above average, gravity began to pull stronger, drawing in surrounding matter. And this is where dark matter played its crucial role. Ordinary baryonic matter was tightly coupled to radiation, or photons at that time. The pressure from light prevented it from collapsing into dense clumps. Dark matter, however, which does not interact with light, was entirely free from this pressure. Consequently, it was the concentrations of dark matter that first began to grow under gravity, forming what are known as gravitational wells. Ordinary matter then began to fall into these already established wells, much like water flowing into a drainage ditch. Thus, dark matter created an invisible framework, a cosmic web of filaments and clumps or halos, onto which visible matter subsequently aggregated. Inside the densest dark matter, halos, gas compressed, cooled, and began to form the very first stars and galaxies. Without dark matter, the formation of these structures would have taken much longer. The universe simply would not have had enough time to form large, complex objects such as our galaxy by the present day. Computer modeling, such as the famous Millennium Project simulation, visually demonstrates this process. In these simulations, scientists input initial conditions corresponding to the cosmic microwave background data and incorporate cold dark matter. The resulting output is a virtual universe whose large-scale structure, the web-like distribution of galaxies, is strikingly similar to what we observe in reality. This provides yet another powerful, indirect confirmation of the standard cosmological model relying on cold, dark matter. The standard cold, dark matter model we just described works brilliantly when we look at large scales, the scales of galaxy clusters and the cosmic web. However, when we begin to examine its predictions for individual galaxies, we run into some disagreements with observations. These discrepancies are collectively known as the small-scale problems. One of these is the cuspy halo problem. Computer simulations based on cold, dark matter predict that the density of dark matter at the center of galactic halos should rise sharply, forming what we call a cusp, or an abrupt spike. Yet observations of real galaxies, especially dwarf galaxies where dark matter dominates, often show a constant density core in the center instead of a cusp. The density increases towards the middle, but then levels off into a plateau. This mismatch may indicate that something is fundamentally wrong with our dark matter model. The other famous issue is the missing satellites problem. Models predict that a large galaxy like the Milky Way should be surrounded by a massive swarm of tiny satellite galaxies orbiting it. Simulations suggest thousands of these small subhalos. However, we only observe a few dozen. Where did the rest go? It's possible that these problems aren't fatal flaws for the theory. For instance, astrophysical feedback, processes tied to intense star formation and supernova explosions in the galactic center might have heated up and puffed out the central dark matter cusp, transforming it into a core. And as for the missing satellites, they might simply have failed to form stars, remaining completely dark and thus invisible to us. Alternatively, these issues might hint that the properties of dark matter are far more complex than we currently assume. For example, if dark matter particles can interact with each other, not just gravitationally, what we call self-interacting dark matter, this could potentially resolve the cusp problem. These outstanding, unresolved questions only make the study of dark matter even more fascinating. Beyond dark matter, there is another dark entity in the cosmos, and it's crucial not to confuse the two. This is dark energy. While dark matter is invisible mass that uses gravity to hold the universe together, forcing objects to attract, dark energy is the exact opposite. It's a hypothetical form of energy defined by its negative pressure, and its job is to push the universe apart, causing it to expand at an accelerating rate. The existence of dark energy was revealed in the late 1990s. Two independent teams of astronomers studying distant supernovae discovered something completely unexpected. The expansion of our universe was not slowing down due to gravity, as everyone had predicted. Instead, it was speeding up. This remains one of the most shocking discoveries in the history of cosmology. To explain this acceleration, scientists had to introduce a brand new component into the cosmological model: dark energy. According to current data, dark energy accounts for about 68% of the total energy density of the universe. The complete energy budget of our reality looks like this. Roughly 5% is ordinary matter, the stuff everything we see is made of. About 27% is dark matter, the invisible gravitational glue, and 68% is dark energy, the mysterious force pushing the cosmos apart. We know even less about dark energy than we do about dark matter. Understanding its true nature is arguably the biggest unsolved puzzle in fundamental physics. The simplest theoretical explanation is the cosmological constant, essentially the energy of empty space or vacuum energy. However, theoretical calculations of its magnitude diverge from observations by a truly monstrous number of orders of magnitude. Dark matter and dark energy represent the two sides of the universe's dark sector. While both are invisible, their effects are diametrically opposed. One gathers, the other scatters, and together they define the ultimate fate of our cosmos. Dark matter isn't distributed uniformly throughout our Milky Way galaxy. Instead, it forms a gigantic spherical halo that stretches far beyond the visible disk of the galaxy. As the solar system orbits the center of the Milky Way, it constantly moves through this halo. This motion can be conceptualized as a wind of dark matter particles blowing directly toward us. It is this very wind that direct detection experiments are trying to capture. The speed of this dark matter wind is approximately 220 kilometers per second. The density of dark matter in the Sun's vicinity isn't particularly high, but it's sufficient for hundreds of thousands, perhaps even millions, of WIMPs, if they exist, to pass through every square centimeter each second. A key feature of this wind is its annual modulation. The Earth orbits the Sun at about 30 kilometers per second. In the summer, for the Northern Hemisphere, the Earth's orbital velocity adds to the speed of the solar system moving through the halo, making the dark matter wind stronger. Conversely, in the winter, when the Earth moves in the opposite direction, the speed is subtracted and the wind weakens. This phenomenon should cause the number of detection events in underground detectors to fluctuate slightly throughout the year, peaking in June and reaching a minimum in December. For many years, the Italian experiment Gamma Libra has claimed to observe precisely this annual modulation signal, and the result is statistically highly significant. This could be the first direct detection of dark matter in history. However, there is a major problem. No other, more sensitive experiment in the world has seen anything similar. This creates a very tense and intriguing situation within the scientific community. Perhaps the Gamma Libra detector is observing some unknown background process that mimics the signal, or perhaps dark matter interacts with their detector, which uses sodium iodide crystals in a unique way that doesn't manifest in liquid xenon or argon detectors. This mystery remains unsolved. Dwarf spheroidal galaxies are small, dim satellite systems orbiting the Milky Way and other large structures. They serve as unique natural laboratories for studying dark matter. This is because they are almost entirely devoid of gas, and their stars are extremely old and faint. The ratio of dark matter mass to stellar mass within them can reach hundreds, sometimes even thousands to one. They are virtually pure dark matter. The visible stars are just rare, faint pinpricks of light that allow us to map the gravitational field. By measuring the motion and velocities of these stars, astronomers can precisely determine the mass and density of the dark matter within these objects. Because dwarf galaxies contain very little baryonic matter and exhibit few confounding astrophysical processes, like supernovae, they are ideal targets for searching for signals of dark matter annihilation. If WIMPs are annihilating, the resulting gamma-ray flux from these clean objects should be far more apparent against the background compared to sources like our own galactic center, which is crowded with other gamma-ray emitters. For years, space telescopes like the Fermi-LAT have been intensely scrutinizing dozens of these galaxies. To date, however, no significant excess gamma-ray emission has been detected. These non-detections have allowed us to set the most stringent limits yet on the WIMP annihilation cross-section. In fact, for many theoretical models involving light WIMPs, this data already rules out the possibility that they constitute all of dark matter. This forces theorists to consider several alternatives, either exploring much heavier WIMPs modeling more complex annihilation channels, or potentially abandoning the idea of self-annihilating dark matter entirely. Therefore, these small and unassuming galaxies play a crucial, monumental role in our attempts to unlock one of the universe's greatest mysteries. What if dark matter isn't just a single particle, but rather an entire dark sector as intricate and complex as our own visible universe? It's entirely possible that instead of just one type of dark matter particle, there are several. Perhaps they possess their own interactions, their own dark chemistry, or even a dark electromagnetic field mediated by dark photons. This conceptual shift opens up a massive field for theoretical construction and could potentially resolve some of the standing issues with the standard cold dark matter model. For instance, if dark matter particles interact strongly with each other, but only weakly with ordinary matter, a concept known as self-interacting dark matter, it could explain why we observe constant density cores at the centers of galaxies rather than the predicted steep cusps. When these particles collide, they would exchange energy, causing the central density peak to naturally smooth out. Models featuring dark photons present exciting detection opportunities. A dark photon might weakly mix with our standard photon, leading to new, extremely rare decays of known particles or generating unique signals in experiments designed to detect light, feebly interacting particles. A complex dark sector could also naturally account for several astronomical anomalies that resist explanation by simple models. For example, it might lead to the formation of dark disks within galaxies or produce far more intricate dynamics when galactic clusters collide. Of course, this remains highly speculative for the time being. Occam's razor advises us not to multiply entities unnecessarily. However, as the simplest dark matter models continue to lack concrete experimental confirmation, the concept that the dark world might be structured far more intriguingly than we first imagined is becoming increasingly attractive. Perhaps we are standing on the brink of discovering not just a single new particle, but an entirely new, parallel universe hidden in plain sight. Let's peer into the future. Which next-generation experiments and observatories are poised to help us unlock the mystery of dark matter? Focusing first on direct detection, even more massive and sensitive detectors are currently being developed. Next-generation projects, such as Darwin in Europe and XLZD in the United States, are planning to deploy detectors using tens of tons of liquid xenon. Their sensitivity will be so profound that they will either successfully detect WIMPs across a wide mass range, or they will hit what scientists call the neutrino flaw. This flaw represents a fundamental limit where the WIMP signal becomes virtually indistinguishable from the background noise created by neutrinos originating from the Sun and other astrophysical sources. If these highly sensitive experiments still come up empty, it would provide compelling evidence against the classical WIMP hypothesis. Moving to indirect detection, significant expectations rest on next-generation instruments like the Cherenkov Telescope Array, or CTA. This observatory will boast unprecedented sensitivity to high-energy gamma rays, allowing us to peer far deeper into galactic centers, searching for annihilation signals. Meanwhile, astronomical observatories, specifically the James Webb Space Telescope and the forthcoming Vera C. Rubin Observatory, will generate incredibly detailed maps of dark matter distribution across the cosmos using gravitational lensing. This data will allow scientists to test the predictions of various dark matter models on small scales with entirely new precision. Finally, future particle colliders, designed to be significantly more powerful than the Large Hadron Collider, will probe even higher energy regimes, opening new pathways for the direct creation of dark matter particles in the laboratory. The next 10 to 20 years mark the beginning of a golden era in the search for dark matter. The combination of incoming data from all these fronts, deep underground, from space, and generated by colliders, provides us with a genuine opportunity to finally lift the veil on this profound cosmic mystery. Perhaps the oddest theory surrounding dark matter involves the hypothesis of so-called primordial black holes. What if dark matter isn't some exotic new subatomic particle, but rather black holes that weren't formed from collapsing stars, but instead originated in the very first moments after the Big Bang? The early universe featured massive density fluctuations. In areas where the density was extremely high, entire regions of space could have collapsed directly into black holes of wildly different masses, ranging from the mass of an asteroid up to thousands of solar masses. These primordial black holes, or PBHs, would be perfect candidates for dark matter. They emit no light, interact only through gravity, and are effectively cold. This hypothesis has waxed and waned in popularity over the decades. Recently, interest has surged again, primarily after the gravitational wave observatories LIGO and Virgo began registering the mergers of black holes weighing dozens of solar masses, objects that are difficult to explain using standard astrophysical models. Some scientists have suggested that these could in fact be those long-sought primordial black holes. However, this hypothesis faces significant challenges. Numerous astronomical observations place extremely strict constraints on the abundance of PBHs within specific mass ranges. For instance, if there were too many of them, we would observe far more microlensing events. They would also destroy star clusters or overheat the interstellar gas excessively. Currently, most mass ranges for PBHs as the primary component of dark matter are already ruled out. Only a few narrow windows remain open, such as those around the mass of an asteroid. Nevertheless, the hypothesis that even a small fraction of dark matter might consist of these exotic objects remains viable and is actively being explored. The discovery of even a single primordial black hole would be a revolutionary breakthrough. Dark matter doesn't just affect how galaxies move, it might also subtly influence the evolution of stars and planets. For instance, if dark matter particles can annihilate, a concentration of them in the core of a star, like our own Sun, could act as an auxiliary energy source. The Sun's gravity constantly captures passing dark matter particles. Over time, these particles would settle into the core, causing their concentration to grow. If they began to annihilate there, the resulting energy release would warm the Sun's core. This effect would likely be tiny compared to the energy generated by standard nuclear fusion, but it could slightly alter the star's internal structure and the flow of neutrinos we detect here on Earth. Dark matter could have had an even more profound impact on the very first stars in the universe. These stars formed at the centers of incredibly dense dark matter halos. Calculations suggest that the annihilation within these protostars could have been so intense that it became the dominant energy source, maintaining the star. These hypothetical objects have been dubbed dark stars. They might have been far more massive and longer-lived than the standard first-generation stars. It's possible that the James Webb Space Telescope, peering into the earliest universe, might be able to spot traces of these exotic objects. Furthermore, there are theories that dark matter could accumulate in the cores of planets like Earth or Jupiter, and its annihilation might contribute a small amount to their internal heat flow. For now, all these ideas remain theoretical, but they beautifully illustrate just how deeply and unexpectedly dark matter might be woven into the fabric of our existence. Let's talk about how scientists are trying to weigh the universe and figure out exactly how much dark matter is out there. Fortunately, we have several highly precise independent cosmological methods that allow us to do this. We've already mentioned two of these, analyzing fluctuations in the cosmic microwave background, or CMB, and measuring the movement and velocities of galaxies within clusters. The third powerful technique involves what are called baryon acoustic oscillations, or BAO. In the early universe, when it was still a hot, dense plasma, sound waves traveled through it, much like ripples spreading outward when you drop a stone into water. When the universe eventually cooled enough to become transparent, these waves essentially froze, leaving a characteristic imprint on the distribution of matter. The result is a specific, preferred distance between galaxies, corresponding precisely to how far a sound wave could travel before it froze. This distance acts as a cosmological standard ruler that we can observe in the modern universe. By measuring how the apparent size of this ruler changes based on the distance to various galaxies, we can accurately reconstruct the universe's expansion history and consequently determine its fundamental composition. A fourth key method is simply counting the number of galaxy clusters. The number and total mass of these clusters are extremely sensitive to the overall amount of matter in the universe, since gravity is what drives their formation. By comparing the number of observed clusters against the predictions of theoretical models, we can deduce exactly how much total matter, both dark and regular, must exist in the cosmos. What's truly astonishing is that all of these completely different approaches, CMB fluctuations, cluster dynamics, baryon acoustic oscillations, cluster counts, and even data from gravitational lensing and supernovae, all converge on the same set of figures. Roughly 32% of the universe's total energy density is matter, and of that matter, 85% is dark matter. This incredible agreement across so many independent observations makes the standard lambda-CDM cosmological model, where lambda represents dark energy and CDM stands for cold dark matter, tremendously successful and robust. For all its enormous success, the cold dark matter model is still an incomplete picture. It successfully tells us how much dark matter there is and how it behaves on the macroscopic scale, but remains silent on its microscopic nature. We still don't know what particle it is. This lack of direct evidence for any specific particle is beginning to cause considerable discomfort among some scientists. Decades of searching for WIMPs, the weakly interacting massive particles, which were long considered the most probable candidates, have come up empty. This failure has spurred an explosion of alternative ideas and models in recent years. The field of theoretical possibilities is now vastly wider. Researchers are exploring models involving extremely light dark matter, such as axions, or conversely, extremely heavy forms. They are also considering the possibility of entire dark sectors that possess their own unique interactions. Some theories suggest that dark matter might decay, albeit incredibly slowly, which could potentially account for certain astrophysical anomalies. There are even ideas proposing that dark matter could be a manifestation of effects stemming from extraspatial dimensions. While this situation might seem like a crisis on the surface, it is in fact a sign of a healthy scientific process. When the older, simpler ideas fail to pan out, it stimulates the development of new, much more creative approaches. Perhaps nature has a surprise in store for us, and the answer to the dark matter mystery will turn out to be far stranger and more fascinating than we ever imagined. We are living in an exciting era where the entire paradigm could shift at any moment with the arrival of new experimental data. It is precisely during these moments that the greatest scientific revolutions take place. Let's consider another intriguing possibility. What if dark matter interacts with ordinary matter, not just through gravity, but through other extremely weak, currently unknown forces? We've already discussed WIMPs, which might participate in the weak nuclear interaction, but what if there are other types of interactions entirely? For instance, some models propose that dark matter particles could scatter off protons or electrons. If this were the case, it could have observable consequences. For example, as dark matter particles pass through the Earth, they might very occasionally collide with atoms in the crust, slightly heating it up. This effect would be minuscule, yet it might be detectable using ultra-sensitive geophysical instruments. Another idea is that dark matter could influence processes in the early universe, which we gauge by studying the cosmic microwave background and the distribution of light elements like hydrogen, and helium. If dark matter interacted with ordinary matter during the epoch of Big Bang nucleosynthesis, the first few minutes after the Big Bang, it would alter the element ratios we observe today. Astronomical observations measure these ratios with extreme precision, placing tight constraints on any such interactions. Searching for these subtle effects represents another major avenue in dark matter research. This requires the combined efforts of theoretical physicists, experimentalists, and observational astronomers. Even if direct detection of particles in a lab proves impossible, we may still be able to learn about dark matter's properties by studying its faint, subtle influence on the visible world around us. Contemplating dark matter inevitably pushes us toward deeper, more philosophical questions about our place in the cosmos. The sheer realization that the material composing us, our planet, the stars, everything we have ever been able to observe, is merely a tiny 5% trace element in a vast, invisible cosmic ocean. That realization delivers a profound blow to our anthropocentrism. This discovery stands alongside those of Copernicus, who showed that the Earth is not the center of the universe, and Hubble, who proved our galaxy is just one of billions. Now we understand not only that we are not at the center, but that we aren't even made of the universe's primary type of matter. We reside on a small island of visible substance, surrounded by an endless dark sea. This forces us to question the very nature of reality itself. What else are we failing to see? What other laws and entities remain hidden from our instruments and our current understanding? The mystery of dark matter is a humbling reminder of how little we truly know. It teaches us humility while simultaneously inspiring us toward further exploration. Solving this puzzle won't be just another scientific discovery. It will fundamentally change our worldview. It will unlock access to 85% of the universe's matter and potentially usher in an entirely new physics that lies beyond our current comprehension. This stands as one of the greatest intellectual challenges facing humanity. And the very fact that we, beings composed of mere ordinary matter, can even ask these profound questions and seek their answers, that in itself is a miracle. Let's return to one of the most compelling pieces of evidence for the existence of dark matter, the bullet cluster. This unique object is often referred to as the gold standard in dark matter research. Officially known as 1E 657-56, the bullet cluster is actually the result of a recent, by cosmic standards, collision between two massive galaxy clusters. This catastrophic event took place about 150 million years ago. When these two clusters smashed through each other at tremendous speeds, their components behaved in distinctly different ways. The bulk of the ordinary, or baryonic, matter within the clusters is not actually found in the stars, but rather in the form of hot, intergalactic gas. During the collision, the clouds of this gas slammed into each other, experiencing immense drag. They heated up to millions of degrees, slowed down considerably, and piled up. We can observe this gas using X-ray telescopes like Chandra, and it is primarily concentrated right in the center of the collision, sitting between the two main groups of diverging galaxies. The galaxies themselves, composed of stars, are much smaller than these gas clouds. Consequently, they shot right through each other, almost collisionlessly, hence the name the bullet cluster. But the real breakthrough comes when we look at the cluster's mass distribution map, derived through gravitational lensing. This map shows us exactly where the gravitational mass is located. Crucially, it is not where the hot gas is. The two main mass peaks are located precisely where the groups of galaxies are, having already passed straight through one another. This confirms that the bulk of the cluster's mass sailed through the collision without slowing down, while the vast majority of the visible matter, the gas, did slow down. This is a direct observation of the separation between dark matter and baryonic matter. This phenomenon is exceptionally difficult to explain using modified gravity theories, which attempt to tie gravitational effects directly to visible matter. The bullet cluster clearly demonstrates the existence of something that possesses mass, yet does not interact electromagnetically. It is, quite literally, a photograph of dark matter in action. In recent years, astronomers have stumbled upon some truly bizarre galaxies that seem to defy our current understanding of dark matter. These are the so-called dark matter-free galaxies. One of the most famous examples is the ultra-diffuse galaxy, NGC 1052 DF2. Observations of the motion of star clusters within this galaxy revealed that its total mass is almost entirely accounted for by the mass of its visible stars. There is virtually no room left for dark matter, or at best, an abnormally small amount. This was highly unexpected, as conventional theory suggests that galaxies, especially such faint ones, can only form within massive dark matter halos. A second, similar galaxy, DF4, was later discovered. At first glance, this discovery appears to be a strong argument against the existence of dark matter. If dark matter is so crucial for galaxy formation, how can a galaxy exist without it? Paradoxically, however, many physicists view this finding as, instead, powerful confirmation of the dark matter model. Why? Because it demonstrates that dark matter is a real, physical substance that can be physically separated from normal matter. If the anomalous rotation of galaxies were merely a consequence of a modified law of gravity, then this effect should manifest in all galaxies without exception. There could be no galaxy where the effect is simply turned off. However, if dark matter is a substance, we can readily imagine scenarios where it might be stripped away from the gas that later formed the stars, for instance, through complex gravitational interactions within a dense cluster. The existence of galaxies with wildly varying dark matter content, from near total absence to total dominance, suggests that these are two distinct components, rather than two manifestations of the same effect. While the exact mechanism for how these galaxies formed remains a subject of debate, their very existence adds an intriguing stroke to the overall cosmic picture. One of the most exciting aspects of dark matter research is the realization that it might hold the key to resolving other great mysteries in physics. We've already touched upon how the WIMP hypothesis ties directly into the theory of supersymmetry, or SUSY. SUSY was originally proposed to solve the so-called hierarchy problem, the fundamental question of why the Higgs boson is so much lighter than theory predicts, and why gravity is so much weaker than the other fundamental forces. Supersymmetry offers an elegant solution to these issues, but it predicts a whole zoo of new particles called superpartners. If the lightest of these superpartners is stable, it becomes the perfect candidate for dark matter. Therefore, the discovery of supersymmetry at the Large Hadron Collider would simultaneously unravel the mystery of dark matter's true nature. Another crucial connection lies with the mystery of matter, antimatter, asymmetry. Our universe appears to be composed almost exclusively of matter, yet the Big Bang should have produced equal amounts of matter and antimatter. Why did matter prevail? Some theories suggest that the very same mechanisms responsible for creating this asymmetry might also have generated dark matter particles. This leads to models of asymmetric dark matter, where the amount of dark matter in the universe is not accidental, but directly linked to the amount of ordinary or baryonic matter we observe. Finally, there is the link to grand, unified theories and string theory. These foundational frameworks attempt to describe all forces and particles within a single mathematical structure. Almost all of them predict the existence of new, very weakly interacting particles that are perfect candidates for dark matter. Ultimately, the puzzle of dark matter is not just an isolated astronomical problem. It is a vital key that could unlock a much deeper understanding of the fundamental laws governing nature itself. Let's circle back to axions and explore why this hypothesis has gained so much traction in recent years, particularly given the lack of signals from WIMPs. As we mentioned, the axion was first conceived to solve the strong CP problem in quantum chromodynamics, the theory that describes the strong nuclear force. This theory includes a term that should inherently lead to a violation of CP symmetry. This violation, in turn, would mandate that the neutron possesses a measurable electric dipole moment. However, experiments show that if this moment exists at all, it is incredibly small, many orders of magnitude smaller than theoretical expectations. The Pechet-Quinn theory solves this dilemma by introducing a new field, the quantum of which is the axion. This field dynamically nullifies that problematic term within the theory. The fact that a particle invented solely to solve a problem in particle physics also happens to be an excellent candidate for cold dark matter is a hugely compelling argument in its favor. Axions, when created in the early universe, form what is known as a Bose-Einstein condensate, effectively behaving like one giant, coherent wave. This leads to some fascinating predictions. For instance, due to their wave-like nature, axion dark matter may form smoother structures on small scales than WIMPs, potentially solving the long-standing cusp problem. Furthermore, these ultralight axions could form exotic objects known as axion stars or boson stars, giant clumps held together purely by their own gravity. The search for axions is a highly active area of research. Besides experiments like ADMX, which look for their conversion into photons, there are several other approaches. For example, axions might be emitted from the sun's core and then convert into X-rays in strong magnetic fields. Axion helioscopes, like CAST at CERN, are designed to detect this conversion. There are also ideas to look for effects that the axion field might have on the spins of ordinary particles, the principle behind experiments like CASPER. The search space is vast, and many physicists believe that this is where the next major breakthrough in particle physics or cosmology is most likely to occur. As we wrap up our journey, let's recap why we are so certain that dark matter exists, even though we still don't know exactly what it is. The evidence comes from a wide variety of independent sources spanning vastly different cosmic scales. First, we have galactic rotation curves. Stars on the outer edges of galaxies are orbiting far too quickly, which strongly suggests the presence of a vast amount of unseen mass. Second is the dynamics of galaxies within clusters. These galaxies move so rapidly that the clusters would have long ago dispersed unless some significant extra gravity was holding them together. Third, gravitational lensing. Massive galaxy clusters distort the light from distant objects much more strongly than their visible mass would allow. The resulting mass distribution maps clearly reveal the existence of gigantic halos of dark matter. Fourth, the cosmic microwave background, or CMB. The patterns of temperature fluctuations in this relic radiation can only be explained if the early universe contained 5 times more cold dark matter than ordinary matter. Fifth is the large-scale structure of the universe. The cosmic web of galaxies and voids we observe can only be accurately reproduced in computer simulations if dark matter is present, having provided the initial gravitational scaffolding for structure formation. And finally, sixth, objects like the bullet cluster, where we see a direct spatial separation between dark matter and ordinary baryonic matter. The totality of this evidence makes the dark matter hypothesis one of the most robust and well-supported concepts in modern science. To discard this hypothesis, we would need to find an alternative explanation that simultaneously accounts for all these diverse observations, an extremely challenging task. This is why the scientific community is overwhelmingly confident dark matter is real. The key question now is not does it exist, but what is it? And so, our long and peaceful journey through the deep darkness of the cosmos draws to a close. We've seen how observing rapid-moving stars and distorted light convinced scientists that an invisible substance must exist, one that accounts for the vast majority of our universe's mass. We learned that dark matter is much more than just dim stars or cosmic dust. It is something fundamentally new, something that defies the known laws of physics. We looked inside the deepest underground mines and the most powerful particle colliders, where the intense hunt is currently underway for elusive particles, whether they are heavy WIMPs or feather-light axions. We understand that without this unseen architect, there would be no galaxies, no stars, and ultimately, no us. But here is perhaps the most astonishing revelation in this entire story. We are searching for a particle. We are building theories based on particles. But what if dark matter isn't a particle in the way we traditionally define one? What if it's a manifestation of gravitational effects stemming from other hidden dimensions, as predicted by string theory? Or perhaps it's a residual field preserved from the very first moments of the Big Bang that simply behaves like matter? The answer to this mystery might not just be the discovery of a new particle, but the unveiling of an entirely new concept of reality itself. This is the central plot twist in this cosmic drama. We think we are searching for a missing brick in the structure of our knowledge, but perhaps we are actually standing on the verge of realizing that the entire structure was built according to completely different blueprints. Thank you for spending this time contemplating the greatest mysteries of the cosmos. I hope this lecture helped you relax and prepare for sleep. If you enjoyed this journey, please subscribe to the channel so you don't miss new stories, and be sure to hit the like button on this video. Now, before you drift off entirely, I want to leave you with one final question. What do you think dark matter truly is? Is it a particle we simply haven't discovered yet? Or is it something so fundamentally different that we can't even imagine it? Share your wildest theories in the comments below. Good night and sweet dreams.